Hey everyone, and welcome back. We're going to do this a little bit different. I don't have a whole lot of time today, but I told you I wanted to get you at least a video a week. Many of you have been craving about diagnostics, and I can't really get into any real details, but I want to go over with you the diagnostic procedure that I've had to follow on this bike to determine what was wrong with it. When we started, we had no idea why it wouldn't run. We just had a few clues. So stick around, and I'll show you how deep diagnostics can go. This is a 2001 Road King, belongs to Robert. Originally, this bike was a Magneti Morelli bike. About 10 years ago, we did a conversion. Actually, we did a lot of work to this bike about 10 years ago, I guess it was. And we did a bit of a mechanical restoration to some degree, went through brakes, everything else. But the other thing we did was the engine, completely top to bottom. And we built, cranking up, and we built it as a 10.5 to 1, 98 cubic inch. Bike runs great. In fact, he's got over 100,000 miles on that build. As far as how we did that conversion, we used a stock, let's see, yeah, that's a stock 2000, well, it would have been a Delphi up to 05 throttle body. And then we used a Daytona Twin-Tech TCFI4, the full closed-loop fuel management system. As you guys know, I worked in development with Daytona Twin-Tech for over a decade. So anyway, we went the Twin-Tech route, and the bike has always run great. Now, when he gave me a call, he said that he had a problem with the charging system, and I still can't figure this part out. It's a little on the bizarre side that he could push start the bike and it would run fine. So we started diagnosing starting charging system, taking a look at the battery. Well, the bike would not start if you use the start button, even with a jump box on it. So one of the first things that we did was to see what our cranking voltage was. There's a little thing with the Twin-Tech ECMs. They don't like to see cranking voltages below 9 volts because it can reset the ECM and put you into a no-start situation. So once we had a jump box on it, at least, we figured out, okay, well, the system's not dropping below 10 volts. It can't be a battery problem, all right? So then we started checking sensors and things, just basic operation. Wanted to make sure that the throttle position sensor was working within its half to 5 volt range, that it was working in the full range. Wanted to make sure that the throttle position sensor was adjusted properly, which is at about 0.4 volts at idle. The next thing is we look at the idle air control motor. We make sure that it's working, the pintle is moving, and that we're seeing elevated steps when cold, roughly about 90 steps. Which would translate to roughly somewhere around 30 to 40 steps when hot. So the IAC was working as it should. So then we wanted to make sure we go to the basics. We want to make sure it's getting fuel. It was actually getting a tremendous amount of fuel and flooding the engine out. So the next step of this process was to see, let's just disconnect the fuel pump, remove the fuel pump relay. All right, let's remove fuel from the equation and see if it just starts with a little bit of ether, right? And that could indicate, yeah, your charging or your ignition system's working, but you've got something with fuel. Maybe it's just flooding it out or something like that, right? So after disconnecting the fuel pump, pulling the plugs, wiping them down, letting it dry out and let all the fuel evaporate from the cylinder, then we spray a little bit of ether in it and try to crank it again. We had nothing. Pretty crazy. Well, then we use a spark tester. We want to make sure that we're getting fire to the plug. Yes, we're getting fire to the plug. And so we know we have air, we know we have fuel, we know we have spark. The next thing that you need for an engine to run is compression. Naturally, we could feel it coming out of the cylinders, but we wanted to do a compression test on the engine to make sure that we were getting compression. Now, it was built as a 10.5 to 1 98 with a cam that's pretty aggressive, so I would have expected to see somewhere around 170, 175 pounds cranking pressure when this bike was first built. Maybe tapping into 180, but again, this was 10 years and 100,000 miles ago over that, so I don't remember exactly what cam I'd put in it at that time. But that being said, we ended up with right at a little over 150 pounds after 5 strokes in both front and rear. So then we know we don't have a compression problem. So this is when things start to get interesting. We have fuel, we have spark, we have air, and we have compression. the 4 elements that you need to have in order for an internal combustion engine, gasoline engine to run. So that led us down another path, which was individual component diagnostics, okay? Pinpoint diagnostics with each, basically with each sensor, okay? Now, one of the interesting things that I did while cranking the bike, I dove into the data, right? Because these systems will log data full time. I logged into the data and I noticed, you know, everything looked fine while the bike was running. And I still can't explain this fully. But what I did notice is that during cranking, the second you hit the start button, I would get a 7,000 RPM spike as I'm cranking. It would read 7,000 RPM, completely off the charts. Well, this is where diagnostics and understanding the full system comes in, and consider this video a bit of a general overview of how this stuff works, right? Well, your crank sensor is a Hall effect sensor, okay? And all of your other sensors on the bike, the intake air temperature sensor, your throttle position sensor, your map sensor, crank sensor, you know, all of those sensors work on a 5-volt reference signal delivered by the ECM. So basically in a Hall effect sensor, the way that they work, like your crankshaft position sensor, is the ECM sends 5 volts to that sensor. Now inside that sensor is, well, it's a Hall effect switch. It's essentially a magnet, right? And then you have notches on the crankshaft. As that crankshaft spins, the magnet picks up the notches and creates a pulse. So you have a positive 5 volt going into the sensor, and then you have the sensor ground. As the crank is rotating and creating that magnetic field, it pulls that 5 volts down and makes it essentially an analog square wave signal that the ECM then translates, and it knows what RPM the engine is running. The other thing is, on all those notches of the crankshaft, if you guys look back at my crankshaft videos, you'll see what I'm talking about. There's also a space. Now that space is essentially skipping a tooth or skipping a notch, if you want to look at it that way. That's how the crank sensor and the ECM knows that the rear cylinder is on top dead center. All right, so the crank rotates, and when it doesn't pick up that signal for that one missing tooth, the ECM goes, "Oop, that's TDC for the rear. We know where we're at." The way the sensor understands what phase you're on, TDC of compression or TDC of exhaust stroke, is the amount of time the crankshaft slows down during the compression stroke. So during the exhaust stroke, the crank moves a little bit, and we're talking, I mean, nanoseconds here, milliseconds, you know. The crank moves a little bit faster during that exhaust stroke than it does the compression stroke. So the reason a bike takes a couple of seconds for it to actually fire is because that ECM needs a 2 or 3 revolutions of that crank spinning. Boom, it sees the notch. It knows right away that that's TDC on the rear cylinder, and then it has to see a couple of more revolutions real quick to know that it's slowing down on that compression stroke. Now it knows what phase it's on. Boom, it fires the plug. That's how they work. So where the ECM is getting the RPM signal from and processing it is, again, from the crank sensor. So when I look at that data and I see 7,000 RPM when I hit the button, I feel pretty certain that we have a crankshaft position sensor problem. Now, I'm hoping you've hung in the video this long, because a big part of this is me making a point. This ECM has incredible capabilities for diagnostic codes. Throughout this entire process, there has not been one single code generated. That's important because codes lead you down a path, but it doesn't take you to the destination always. So understanding pinpoint diagnostics are very important. So I'll continue. Once I established the fact we had the 7,000 RPM spike and realizing how much fuel it was dumping, okay, well, the ECM thinks it's running at 7,000 RPM. It's going to dump a ton of fuel and flood it. Plus all the other sensors, the map, the fuel delivery, the spark, everything else would be off, acting almost like a mechanical cam timing issue, the way it would pop and backfire and things like that. So then the next thing we do is I grab my oscilloscope, right? And what you can see with an oscilloscope, when you hook it up, as I've done here, to your crank wires, your crank sensor wires, you can see that square wave, and it looks just like this. And then you can see the notch in the crankshaft. And you see it, and you see it, and you see it, and there's the notch. So when I hook up my oscilloscope, I saw my square wave in the notch. But then I realized that we only had 2.5 volts as a result coming out of that sensor. We should have had a square wave that was 5 volts, only 2.5 volts. So then the next thing we do is we go straight to the 5-volt sensor power wire coming off of the ECM, and we realize we're only getting about 2.5 volts. So if you remember, I said the way the Hall effect sensor works is that that magnetic field is pulling that voltage down. Well, if we're only getting 2.5 volts and it's not pulling, and it's pulling it down, the engine will see an exceptionally high RPM, 7,000 RPM. So in short, I believe we have a bad ECM, because coming directly out of the ECM, we're only getting 5 volts, or excuse me, we're only getting 2.5 volts when we should be getting 5. The other thing that if for example that ran to 5 volts, the next thing that I would do is check sensor ground. Okay, we did pull the sensor, and it physically it looks absolutely perfect, and unfortunately at 2.5 volts. So we're going to see if the bike will fire up. So what I have done is, and I want to show you guys what the wave, I'm going to show you what the wave looks like while the bike is running, if I can keep it running at the same time. What we should see, oh, it powered off. Let me get us powered back up here. So I want to show you guys what that waveform looks like, and then what I've done is just grabbed a known good stock ECM out of a 2005 something. Okay, just a Delphi ECM. So I've unplugged the stock one, or excuse me, unplugged the TCFI, plugged in the stock ECM, and then this is what our oscilloscope looks like. We're going to be looking at channel number 1 here, which is where I have it connected. So we're going to set our system voltage, or excuse me, our voltage right here to 5, and this should produce a waveform if the bike runs. And then we'll be able to see the notch there as well. So hang with me for a second. Guy, you want to give me a hand?
Sure.
All right, so what I want to do, if you'll hit the compression releases.
Okay.
This is a trial run. We might get embarrassed on camera. So our theory is that it is a bad ECM. So we have the ECM plugged in. You can see I'm holding the exhaust and such. We're dealing with a cold engine here. How much you want to bet on it?
I always lose.
No, you don't. Okay, so we're going to say bad ECM, and we're going to give it a shot. And what I want to do when I crank, if it'll crank, if you can just work the throttle for me,
sure,
to keep it running, because I want to show them what the waveform should look like.
Gotcha.
And then we're going to sign off. As a matter of fact, I'll let you do the honors. Let's see if it'll.
Okay, everything.
We got
ready?
fuses but hooked back up and everything.
Yep.
All right, let's go ahead. Fingers crossed. All right. Bad ECM, brother.
Absolutely.
I hate it for Robert, but it's a bad ECM. So anyway, if you could see, I don't know if you could see that on the scope or not. You saw the squiggly lines. Well, the squiggly up and downs is each time the crank sensor is hitting that tooth. When you saw the space in between is that notch. So what we have is a waveform that looks as it should, actually operating 0 to 5 volts, or excuse me, 5 volts, and we put an ECM in it. So we've got several hours worth of diagnostics into determining that it's just an ECM. We got to remember the age of this bike. We did not put a brand new wiring harness in it, and it's got 140,000 miles on it, I think.
I think so.
Yeah, somewhere around there. So we have a wiring harness that was installed in 2001. We have a 20-year-old wiring harness. So you never know. We could have gotten lucky instead of just throwing parts at it. Maybe there was a pinched wire in the harness somewhere. Maybe, it could have been any number of things that we could have found quickly. So some diagnostics sometimes is required. And you guys have been wanting a diagnostic video. There we go. That's one anyway. We got a lot more coming. Thanks a million, guys, for watching. I appreciate you very, very much. Thanks to all of our channel members. Thanks for all your comments and everything else. Excuse me. It's great to see you guys again. So have an awesome weekend, and we'll talk to you soon. Take care of yourselves and each other. Have a good one.